I'm going to give y'all a couple of warning shots, and the first thing I want to do is thank the foundation for the third year of this symposium. This has quickly become one of my favorite meetings to attend each year. I'm habitually not somebody who enjoys attending meetings, but this is one I certainly look forward to, and that's a testament to Dr. Ng's vision about what he wanted this to be. And I thank each of you for being here today, helping to make that vision a reality. I'd also like to acknowledge the support that the Kenneth and Carolyn McDonald Ng Foundation has provided to our research programs as well as the programs of others in order for us to make some fairly rapid progress in certain areas that historically have been quite undervalued or underfunded in the research community. And I think that that has been an immediate and will be a lasting impact of this effort. So I want to get those acknowledgements out of the way early. The other thing I want to do is give y'all a heads up as an audience. I have approximately 40 minutes or so to talk. Is that right, Dr. Karstens? And I have 733 slides, approximately. And so I'm going to actually go through my slides pretty quickly. It's going to look like a movie if I do it right. And so that'll be really entertaining for all of us. And I have quite a few data slides, but my goal really is to tell the big story today, not necessarily to describe each seedlet on each weed. And so as we go through, if there's something that I don't give you much detail about, make a note of it and we can sure discuss it afterward. You'll notice a lot of names listed on the title slide here. I believe with one exception, all of these graduate students are in attendance today, as well as other members of our team that maybe didn't have direct responsibility for one of the projects that we're reporting. But if you have really hard questions, I will call on them, and they are prepared for that. Not really, but I probably will sick y'all on them a little bit during the break. So I also want to thank their dedication and hard work. So I like consistency, and so you're going to see a few things that you've seen from us over the last couple of years. We've gone into this with a mindset that there is a global opportunity for the beef business, that the anticipated increases in the human population and the anticipated increases in the affluence level globally will expand the demand for protein by up to 100% over the next, let's say, 35 years. That's the target date that everybody has provided. And that this huge opportunity exists in no small part for United States agriculture. There are some real challenges, though, to achieving access to that growing demand through expansion. Capitalization requirements have increased almost exponentially. In the United States, particularly, capitalization requirements think, how much does an animal unit cost in land? What's the land value, right, of an animal unit today in the United States versus 20 years ago versus 50 years ago? And that curve is remarkably steep. In Texas, in the last 10 years, now think about that, at least 9 of those years were below average for rainfall, and about 5 of those years were exceptional drought. And during that time, the average rural land values, productive land values, and not farmland, ranch land in Texas, have gone up something over that whole time span, something in the neighborhood of 170%. So clearly there's some non-agricultural factors driving that capitalization requirement. Land availability is decreasing. We have perceived, at least, expanded risk in weather and markets. And we have this new form of risk in public opinion that may create some significant barriers to our ability to meet those goals. So when we have challenges, we need to create solutions. So our mindset has been, how can we create sustainable solutions to these challenges? Sustainable solutions, as we've defined them, have to be economically efficient. They must be environmentally or resource utilization efficient. And they must be socially and ethically acceptable. And finally, they must be resilient to shock, or they must confer the property of resilience on the systems that we're interested in. How can you withstand severe drought and remain in business? That's resilience. And you might recall from a talk we had here last year that we worked a bit to describe some of these factors and maybe to talk about some ways to measure those. It's not my goal to repeat that this morning, just to remind you of it. And so here's kind of I'm very visual, I like pictures of things, so this is my picture of how a desirable solution set in these systems would work, right? That all four of these factors are integral to the function of the system. And I mean, I'll admit, Microsoft created the little gear thing, and I'm confident that each of you have used that in a presentation at some point in your careers. And but the little spring is mine, so I'm going to trademark that. So if y'all want to use it, send me a check, and I'll appreciate that a lot. But our purpose, and this is programmatically, but also a bit my purpose today, is to foster innovation. And as I mentioned in my opening remarks, this symposium has consistently had that term in its title, right? Innovation in production systems. And so as we've thought about this, we want to find a mechanism by which to foster innovation, not to be married to one particular concept, but how do we foster innovation in production systems in order to achieve these goals that are related to that solution set that I described previously. We've actually kind of gone a step further to some degree with impetus from this program and from the Foundation's support. And I would encourage you, if you wish, to go to our website and find the little button that says Sustainable Solutions for Beef Production Systems to give you an idea of how we, at least at Texas A&M and the Department of Animal Science and Texas A&M AgriLife Research, are trying to frame our programs around these areas. So that's my plug for the morning. So how has our team approached this challenge of innovation in intensive cow-calf production systems in order to meet this global demand for protein that we believe to be such a boon to American agriculture? So here's our mental model, if you will. So we want to conceptualize possible solutions, right? This is like a brainstorming event. And then from those, we want to identify those that appear on the surface to be viable or at least be interesting and develop some sort of a model. And this could be a spreadsheet. I personally like blank sheets of copy paper and Sharpies. The graduate students will tell you if you come to my office and find me, which is not common, that you're likely to leave with a scratch sheet of paper covered with Sharpie drawings. And so the development of models in some framework with maybe not a lot of sophistication is an important part of evaluating possible solutions. Because from those models, we begin to envision where the leverage points are. Where can you really have an impact on the system to move it? Or where might there be significant barriers to implementation of a certain solution? And on either side of that, that creates the opportunity for us to conduct research. And so as researchers, our activity is mostly in this little circle. But we want our mindset to be mostly down the middle of the frame, right? That the research results then should inform our ability to develop sound strategies, to create decision support system tools for managers. But those tools also require ongoing validation, and when we find out something's wrong, we should fix it. If we find out something's really wrong, we need to reevaluate the research that led us in that direction, and maybe even go all the way back to the model or rethink the concept. So there's some, we'll say, negative feedback loops in our thought process, although I don't want it to be a negative concept, right? I mean, most of y'all probably are right the first time, all the time. I've lived a life of being wrong most of the time, right? So it's important to me that we have some ability to go back and correct our errors. And so really this is how our team has tried to approach this problem. So I'm going to talk a little bit about the framework. And this is part of the conceptualization part. What frame are we going to put things in? And our frame has been that of an existing operation. So a cow-calf operation that currently exists and operates as an extensive operation and has the goal of expansion and therefore, but cannot acquire more land in order to expand. So this is kind of the framework that we've built mentally. And so to do that, we really are talking about increasing land utilization. And as a sidebar, I'd say we kind of set ourselves an initial target out of thin air, right? We made it up. I'm just to be honest with you. We just made it up. But we said we want to increase land utilization or the productivity per acre by 35%. And it wasn't totally out of the air because remember we said that there's going to be at least a 70% increase in protein demand over the next 35 years. And maybe half of that we can get from Dr. Herring, genetic improvement, or other technologies, more classical production enhancements, right, that have been a hallmark of our industry for many years. So where's the other half going to come from? Well, we're going to have to get better at using what we have. So that was part of where our 35% target came from. We've also framed it as that as it currently exists, this hypothetical ranch is in balance. In other words, they're utilizing the calories, the feed that's produced by the ranch exactly. Right? They're perfect managers, just like y'all. Not like me. We also kind of have this mindset of calories being the currency of the system. And if you were here at this symposium 2 years ago, you heard us talk specifically about that. What's the value of a calorie? And I think that's a convenient way for us to think about these aspects of the system. And then finally, that if we create solutions that are effective enough, they will be at least in part transferable to other systems. So it may be that we're talking in our mindset about confinement of cows in a more intensive environment for only a portion of the year. But if our solutions for that are viable, it should be at least in part transferable to a system in which confinement is 100%. Okay, so it's not exclusive of that, that's just not where we start. So developing the model, again, I like consistency. You've seen this before, and you'll recall if you saw it before that you couldn't read it then either, and that's okay. This is just a budget template that we developed in order to give ourselves, this is part of our model, right? How many dollars flow through the production system, and this is a little more readable subset of those numbers. The numbers here aren't important. I'm just trying to communicate to you that the budget is one aspect of the model, right? We built the budget before we built the system. And we also tried to model the energetic or the caloric demands of the system and how those might change should we implement certain types of solutions. So these slides you've seen before if you've been the last couple of years to the symposium. If you haven't, you can find these in the proceedings papers from the last 2 years. And again, our main point here is, remember, we had this ongoing operation, and there we said, okay, the energetic demand from the ranch is 5,200 megacals per year per cow. Okay, the ranch has to produce that much forage, for example. But in our system, we're going to take that and we're going to reallocate it. Instead of taking all year to utilize that, we're going to utilize it all in a fraction of the year, which is going to leave us a part of the year where we have to rely on exogenous calories. But by doing that allows us to expand head count by, in this calculation, 39%. And some others that we've done, slight modifications, it may be closer to that 35% that we were initially aimed at. Make sense so far? And the good part is this is just thinking about it, right? We haven't had to do any work yet. This is my favorite part, by the way, in case you couldn't tell. And so we kind of hook those things together, right? The initial budget plus this reallocation and the cost of that reallocation. We had to purchase those additional calories. They have a cost. And in our model then, we can identify that we have added substantially to the cost of the business, right? Which is a leverage point. So how do we, if we know now that was a significant move, the needle moved a lot in the system through our reallocation, and the way we saw the needle move was on feed cost. So now we start to develop solutions around that leverage point of feed cost. And we've envisioned a couple of ways to do that. One would be, how do you just make the feed better? Make the feed more valuable, or reduce the cost versus value ratio of the feed, right? And the obvious way to do that is formulation. In fact, probably what was one of the sparks of this symposium is the fact that many of you have been utilizing higher energy density rations in cows for a long time. Now, in our group, a decade ago, we had a lot of interest in that, but with a completely different target outcome, right? How do we upgrade packer cows was the question for us at that time. So this idea of increasing caloric value through formulation is not new. If it was, there wouldn't be any nutritionists in the room because we'd just be starting out, right? But there's a lot of nutritionists here today. So the other, though, is not through formulation. What other methods or techniques might we utilize to increase caloric value of the feed through enhancing its utilization? So think digestibility. The second kind of broad area relates to the question Dr. Carson's asked just a moment ago. Can we reduce maintenance requirements of the cows, but through management rather than through genetic selection? Now, many of you know I have some background interest sort of in stocker operations, and because of that, I kind of tend to work from a paradigm where the genetics I have are the ones I got. They're not changeable, right, in the short run. And so how do we do other things to try to manipulate those requirements in the short run? So from that, we identify a couple of feasible solutions, or at least a path toward them, and then we begin to test those. And so now I'm really going to go quickly through this if I can. We created sort of a general experimental model where we conduct feeding trials using 50 to 60 cows. 4 treatments works really well for us because of our space and resource assets in an individually fed kaolin gate system. And so, you know, I don't really take pictures much, so I'll credit these to the team that provided them. And in the background there, you can kind of see the kaolin gate. So these cows are in a kaolin gate pen. And we have also then tried to do companion digestion trials using cannulated steers in metabolism crates or stalls, but using treatments that are common to the feeding trials, right? So a pretty classic research model here. And we've done a series of studies over the last 2 years. We've been pretty busy. So the first, and you've seen initial reports from this last year, so I'm not going to spend a lot of time, but was looking at 2 levels of energy density fed at 2 levels of intake related to NRC-based requirement or predicted requirement from the NRC model. And it's important for me to point out to you that even when we were feeding these diets at 120% of the NRC predicted requirement, those cows were still technically restricted in intake, right? They weren't consuming feed ad libitum. And though, like I said, the results from that feeding trial were reported last year, and the high point of that was that we observed a 26% reduction in the apparent maintenance requirement of those cows by feeding a higher energy density ration. So simply with ration formulation, we were able to achieve a significant reduction in maintenance requirements and therefore the cost of feed or caloric delivery in the system. We also had an observation there that reducing intake had the secondary benefit of increasing the caloric value of the diet. So on one side, we're talking about changing the requirements of the cow. On the other side, we're talking about the diet's capacity to deliver calories. And we did the follow-up digestion trial to that study subsequent to the field trial. I like to do things backwards, do the fun part first and the other part last. But in this digestion trial, we were able to much more clearly elucidate this interaction between energy density of the diet and intake level, such that reducing or restricting intake from 120% to 80% NRC requirements really had negligible effects on measures of digestibility or energy provision when we fed a low energy dense diet. But when we went to the higher energy density diet, we got substantial increases in the value of that diet or in its capacity to produce calories. And so if we think about also that benefit that we observed in reduction of maintenance requirements by using the higher energy density diet, we see a synergy there, right? So we envisioned two possible directions for solution: increase caloric value or reduce maintenance requirements. And with this strategy, it looks like we get the benefit of both. That's a real win, right? If you can get both of those by virtue of that interaction. We thought then, well, there's maybe some other ways to augment caloric value of the diet, and ionophores are a long proven technology in order to do just that, to increase the effective or apparent energy density of the ration without actually affecting its chemical properties, but by changing its digestion, presumably. And so we did a similar study in which, or a pair of studies, in which we had a 2x2 factorial, 2 levels of intake, again, 80 and 120% NRC requirement, utilizing that high energy density ration from the first experiment, with now the second factor being the inclusion of an ionophore. We did use Meninsen for these studies at 0 or 200 milligram per day. And the Meninsen was provided by hand each day in basically a small package supplement like a premix. It's important for you to note that that premix was 100% distiller's grains. So we made a little Meninsen premix out of DDG and then hand added a fixed amount of that to the ration each day to achieve the final formulation. And in the control cows, we did the same thing. We hand added some additional distiller's grains so that we had the same sort of mixing situation for both treatments. And in this one, now I know you can't read all these numbers, and that's okay because you don't need to see them all. We're just kind of hitting the high spots here. One thing you will see here, though, is that intake level, 80 versus 120% NRC requirement, had significant effects on essentially every measurement here. And these are all related to the caloric value of the diet in some way or another. However, the inclusion of Meninsen had no statistically significant effects on these measures. Now, don't be too surprised by that, because this isn't saying that Meninsen didn't do its job. This is just saying that we don't really expect Meninsen to increase digestibility. We expect it to alter fermentation profile, and that is the sort of caloric enhancement that the ionophore confers, right? So these measurements really aren't capable of describing that benefit, and therefore we don't really see that effect. Where we thought we would see it is here. And so I mentioned to you, I didn't show you data, but mentioned to you that in the first trial, we observed about a 26% reduction in maintenance requirements between the two, using the high energy density ration. And I should point out to you that in that study, the low energy density ration, our observed estimates of maintenance requirements were almost identical to the predicted values from the NRC, okay? In this study, there was really no statistical difference between our estimates of maintenance requirements due to ionophore inclusion, but the average of both treatments was about an 18% reduction in maintenance requirements relative to NRC. To the NRC base requirement, and about a 24% reduction below the level that the model predicted, including environmental effects, age of cow, et cetera. And so I'm going to use the 24% and say, hey, we got the same result twice, and that's never happened in my career. I've never gotten the same result twice doing a study, so we feel pretty good about this. We feel like this is pretty real. But again, no real effect of the ionophore. Why not? Did the ionophore really not do anything? Well, again, our sampling technique here probably really wasn't capable of discerning that effect. We also had this other interesting response. And so this is percentage change in body weight of the cows over the duration of that trial. And what you can see here that I have circled is you have one group where between days 14 and 28, and recognizing all of these cows would have started at 0, because this is relative change in body weight, that from day 14 to 28, this group lost some amount of weight and then stabilized throughout the rest of the period. Whereas this group had a much more gradual decline and didn't really achieve stasis until day 42. Well, this is the group fed 80% of requirement with the ionophore, whereas this group received 80% of requirement, but no ionophore. Now, the fact that they both achieved stasis after only about a 1.5% reduction in body weight, which is consistent with fill equalization, would indicate that both of those sets over the long term were effectively fed at maintenance. About 20%, but at 80% of anticipated requirements, right? So like a 20% reduction in requirements, which is consistent with our expectation. But why didn't the ionophore perform differently? Well, it did. You can see here that it actually mitigated weight loss initially. The problem is that when you think about what that means in terms of maintenance, it means that those animals' rate of reduction, so we're assuming that maintenance requirements start here and are actually reduced through this management practice, the rate of reduction in those requirements appears to be slower. So the ionophore, by doing exactly what you would predict it does, supplying effectively a bit more energy to the animal, slows their acclimation. And so this is our hypothesis, right? Now, that hypothesis can only be true if the ionophore actually had the effects we expected it to have. And I'm not going to actually show you results from the digestion trial because they look exactly like you would expect results from a Meninsen feeding trial to look. No real effects on digestibility, every effect on fermentation profile that you would anticipate. Propionate goes up, acetate goes down, et cetera, et cetera. So the ionophore did what it was supposed to do. It's just that the outcome, even though we can rationalize that that would be an expected outcome, wasn't what we had predicted. And so we think that perhaps we should reevaluate the timing of ionophore application in this system and wait 2 to 4 weeks after transition to the high energy density ration before we apply it in order to really secure the benefits of the technology. So far we've talked about 4 experiments in a relatively short amount of time, so I'm going to try to keep pace here if I can, and talk about a 5th experiment. Because of this reduction that we've so far consistently observed in maintenance requirements, we wanted to be better capable to produce decision support tools and therefore predict the rate of reduction or the quantity of reduction in maintenance requirements. And so we set this experiment up a bit differently. Rather than using the factorial structure, we used this graded structure ranging from 70 to 115% of anticipated NRC predicted requirements. And this, recall that in our previous experiments, we were using 80% and 120%. So we aren't really interested in going much above the range. We would like to go continuously lower. So that's why we dropped down to 70. And to be honest with you, we're thinking, if this works, we're going to 50. But we'll see if it worked or not. So the diet used here was similar to that high energy density ration used in the previous 2 trials, with some slight modifications in order to accomplish the experiment and achieve these targets. And so rather than using a completely static ration throughout, the adjustment here was really made between, these cows were effectively fed a fixed level of roughage with a varying level of concentrate, okay? And I'll show you the diets here in just a second. The deviations aren't substantial, but you need to know that. And the other difference here is the previous 2 trials were cows that were essentially in mid-gestation to early 3rd trimester. And in this study, we purposefully did it across the 3rd trimester of gestation up until calving. In fact, Miss Early here in the audience and her team attended calving in every one of these cows and fished calves out of the pen in order to collect colostrum samples from the cow. And there are other aspects of this trial that I'm not really going to discuss today that are related to calf health. again, lots of numbers, so don't worry too much about the details here. Here are the diets that I mentioned, and you can see the proportion of wheat straw going down as we're trying to hit a higher target level of the cow's requirement, and the proportion of corn going up. But if you multiply the percentage of wheat straw by dry matter intake way down here across the board, you'll end up at about 5 pounds of wheat straw per cow per day, right? So the adjustment is really in the concentrate portion of the ration. If we look at the results from this trial, the part that I want us to pay attention to here is our measures of retained energy conducted with the same methodology that we've used before, which is based on ultrasonography for body composition with well-established equations to predict body energy, and then heat energy by difference. And we do have linear effects of diet on both of those measures. And if we look at the span here between heat expenditure across that range, it's about 24% lower in the 70% group, okay? And if we think about the span between 70 and 115, that's 45 units, versus the 80 and 120 from our previous studies, 40 units, the reduction per unit is very consistent across the trials. So we think that this reduction in maintenance requirement is both consistent, and because of this study and the graded structure of treatments, becomes very predictable. The problem is it's linear, not quadratic. That means that we can probably go lower. How much lower? I don't know. I guess we'll find out next year, right? The other thing that we were actually able to capture from the other experiments as well, but I did not report to you today, is estimates of measures of birth weight in the calves. And I can tell you that from the previous 2 trials, there were no differences, no statistical differences in calf birth weight following those trials. But recognize that those trials were conducted in mid-gestation, and the cows went back to common diets after the experiment for the last trimester, and so perhaps you wouldn't expect much deviation in birth weight in those experiments. In this one, since the cows were on treatment until they calved, we were able to detect a linear effect on birth weight, going from 32.5 kilograms up to almost 37. So this is actually a pretty small deflection in birth weight, but gives you some idea about the level of control really that was exerted in this experiment. And if you just look at the numerical data, you'd say the real driver of this difference is at the 70% group, which had a numerically and statistically lower birth weight than the other groups. However, a short 30 days or so after calving, those differences disappear, and for the remainder of the calf growth period, we'll wean these calves next week, 3 weeks from now or so. But Nessie has weighed these animals repeatedly throughout their pre-weaning existence, and again, by day 30, the differences were gone and will be gone still by weaning. So really no long-term effect there. So I've talked about a couple of leverage points. We want to hit one more really quickly, reduction of fixed costs. Again, in our budget model, fixed cost escalation is one of the leverage points that was identified. How am I doing on time, Dr. Carsons?
Good, 10 minutes.
Excellent. And so how do you reduce fixed costs typically in any business, or in the cattle business? Well, you increase volume, right? Increase headcount, keep the hotel full. And so that's a fundamental intensification strategy. And so our forage reallocation that we talked about, and we're calling this the 2-to-1 system. So, 2 periods on pasture, 1 period in confinement, right? And in ours, that means 4 months in confinement, 8 months on pasture. And by doing that, we increased headcount, we said around 39%. And so by default, we're reducing the land cost per cow by approximately 39%, simply by adding headcount in the system. So we get some advantage on the CapEx in these systems. But there are some other areas where we're probably going to add some capital expense through infrastructure and facilities and equipment that are necessary to operate this system. And so a strategy that we devised in order to increase the utilization of that infrastructure, so think about this, we're running 1,000 cows. We decide we want to put them in confinement for 4 months a year. So we build pens to hold 1,000 cows for 4 months a year. Well, that's 8 months of a lot of idle steel sticking up in the air, isn't it? It doesn't make a lot of sense to do that. It makes more sense to try to increase that utilization from 33% to 100% and reduce that infrastructure cost, but also probably reduce the overall equipment requirement because I'm only feeding 1/3 as many cows at a time. And so the way that we are attempting to test this solution is with the development of an entire production system that we have named Red, White, and Blue. And in this system, we have developed 240 heifers to go into one of 3 subgroups based on calving date. Note that these calving dates are in month 1, plus 4 is month 5, plus 4 is month 9. So 4 calving groups, 120 days, conveniently apart. And our framework, remember, is that we're going to put cows in confinement for 120 days per year, from weaning until 30 days pre-calving. So we've built this system around that hypothetical model that we developed and put it into production. And this will be, over the next number of years, our platform for system-level evaluation of solutions that are devised. In your proceedings, there's a calendar that I'll show on the screen here in a minute, but it may not be very readable to better describe this system. And then the question, why red, white, and blue? Well, there is this. And I tried to call it maroon, white, and khaki. But actually, the cowboys at McGregor named it red, white, and blue because, as cowboys are wont to do, they will name whatever they choose to name, and that is the name it shall be called. And actually, red, white, and blue works out pretty well. So here's the schema for the system, and it makes a little more sense to me. I'm a picture person, so this makes more sense to me. So the first group is calving here, really, let's call it January calving. And then we have sort of a normal management calendar within each group. So branding or calfhood vaccination period, a very short 42-day breeding season, followed by pre-weaning of the calves at their side, and then weaning of the calves and entry into the confinement system are simultaneous. So we put the cows through the pens at weaning, we sort the calves off, the calves go to one set of pens to dry out, and the cows go to another set of pens to stay for 120 days. Okay? Now, conveniently, at the time of pre-weaning and or weaning, and we've actually elected to do it at pre-weaning, is when we will do pregnancy determinations. Because at that point, then, we can pre-identify cows that failed to conceive during this short breeding season. And as we wean the calves, they can immediately be rolled to the next calving group for another opportunity to breed 4 months later. And in some work that was done at the King Ranch, this feature, right, this capacity to sort of preserve the cow for one more round, if you can do it in less than a year, so she doesn't have to miss an entire production year, is over the long haul more financially stable, reduces replacement costs in a 2-herd system by as much as 53%. In a 3-herd system, that reduction is likely to be greater because the gap is that much shorter, right? 4 months versus 6. We don't have data to support that, but that's why we set it up that way. We put a business rule in place that we'll never keep a replacement female out of a cow that has rolled 1 time or more. And we put a second business rule in place that if the cow misses here and rolls, and then misses here and rolls again, one more, so she can roll twice before she gets back to her original group. If she ever gets back to her original group, even if it's several years later, then that means that cumulatively in her life, she will have missed one whole production year and therefore must be culled. Okay? Now, I will be honest with you, that sounded really good, and it has created a significant record-keeping challenge. Because, I mean, you all probably have a record system and you record conception, right, on every cow for that year, once. But what if you need to record it 3 times? How do you put that in your book, right? So it's actually created a challenge for us that probably have to hire a computer scientist or something to fix it. I don't know. But we just added columns to the spreadsheet. That's how we fix everything. And so there should be some fairly obvious means through this system to reduce capital expenditures. And again, I mostly wanted to inform you that we have this system developed. It's in production. We will finish our sort of first complete production year here in a few months. But we started with a single calf crop of heifers to do this, and so it's taken us about 2.5 years to get to this point in development of that system. Okay, I have to go really fast. So there are also some barriers to implementation of any of these solutions. Poor feeding logistics is a large barrier. The diets that we initially were most tempted by utilize some very poor quality roughages and some very low bulk density byproducts, and that makes feeding logistics really challenging. You can ask the graduate students that have had to manufacture these rations that feeding logistics are really bad with some of these diets that we've put together. And so we wanted to find a mechanism to predict the bulk density of finished feeds. Some of you may be aware of a secret proprietary formula to do that with, but there are no widely available mechanisms to do that. Part of that is because of the problem of interspersion during mixing. So you take a fluffy thing with lots of holes in it, and you mix some dense stuff in it that can fill the holes. That interspersion or packing problem is considered to be the hardest math problem in the world. So we decided to solve it with an extra column and no, I'm just joking. We've solved it with a chunk of PVC and a piece of sheet, plate steel cut into a circle. And borrowed this from this idea from our colleagues that are mostly involved in forage management and the concept of the rising plate meter. So we developed the falling disk meter to evaluate bulk density and compressibility, if you will, of feed ingredients. And by doing that, we could estimate the interstitial space, and by knowing then the bulk density of both or several ingredients plus the interstitial space of the least bulky ingredient, we can predict interspersion reasonably well and estimate the final bulk density of the finished feed. And so here's just some of the common ingredients that we use, their bulk densities with our cheap and easy method. And I can tell you that where it has been reported, bulk densities for some of these commodities, our method predicts them almost exactly with other methods. There really aren't published values for chopped roughages because every time you do it, it's different, right? And so you need a method where you can sample repeatedly. When we put that into a prediction tool to predict maximum payload as a function of roughage inclusion in the diet, and our mixer is a Book 800 cubic foot mixer, we estimate that the real capacity is always about 10% under the Book, right? Because the screws are in there and they take up space, and that's not accounted for in that Book capacity. But you can see the difference between using chopped alfalfa versus chopped wheat straw based on these equations on the maximum payload achievable in that 800 cubic foot mixer wagon. And so at 25% roughage inclusion with wheat straw, your maximum payload is about 2 tons. Well, that doesn't go very far, right? And so to manage the logistics here, we're going to have to find a way to either continue to reduce the roughage inclusion, which creates another set of risks, right? or find some different delivery techniques in order to overcome that roughage challenge. And so one option there is to deliver the diet as separate components. So deliver the roughage separately from the concentrate package. And so we conducted an experiment. Again, this one will be a two-part experiment. We've done the digestion trial, but not the field trial comes as soon as we dry some cows off this fall to place them into the system. And we had 4 treatments there, the TMR, delivered as per our other experiments, or the roughage component with the supplement package being fed 2 hours before the roughage with the supplement being fed 2 hours following, or the roughage with the supplement being fed 12 hours after. Or I guess you could say the supplement being fed 12 hours before, because it really doesn't matter. You feed hay in the morning and supplement in the evening, right? And so in this trial, and the obvious concern here is, are we going to create an insult, right, with this large package of energy-dense feed without roughage inclusion at that time that's going to create a metabolic challenge for the cows? And so there's lots of data, obviously, from this experiment. I'm showing you one slide. And this is pH across the time relative to the time that the roughage was fed. And this line that you see up here is the system in which the supplement package was fed 12 hours following roughage feeding. But if we scale that to relative to the time that the concentrate was fed, those lines fall right on top of one another. None of those pHs ever fall below 6, and we would believe this then to be a potentially viable method to help enhance feeding logistics through Payload. So that's really the data that I wanted to report to you today. I've reported to you on, I think, 6 or 7 experiments in a fairly short period of time, kind of trying to hit the high spots. We have a series of experiments planned for the upcoming year. We've been very fortunate to be able to utilize funds from the foundation to leverage against other programs that are available to us. And by doing so, we've actually been able to turn every dollar from the Kenneth and Carolyn McDonald Ing Foundation to support our research programs into 3 total dollars to support those same programs. And so that's allowed us to expand our capabilities quite widely and to do these follow-on experiments related to these initial efforts that will allow us to go on and create decision support tools in a fairly rapid manner. The question of calf health is one that is of continuing interest, and I mentioned we will have initial and preliminary data related to the titration study that we did show you the performance results for. And so we'll perhaps be able to make some report on that by next year and continue to look in that direction. With that, I will stop. I thank you for your attention to my movie, and we look forward to trying to answer any questions you might have.
All right, thank you, Dr. Sawyer. We're due for a break, but let's take a few minutes for a couple of key questions.
You know, one of the things that has surfaced all the way through our meeting so far is the decreased maintenance energy requirements of these cows where we're feeding them limited amounts of high energy dense diets. And we've asked the question, is that genetic or is it's something else? Webster and Reynolds and others have taught us over the years that the predominant factor as far as influencing the partitioning of metabolizable energy into retained energy and heat energy is the size and metabolism of the portal drain viscera or gut tissues. So we take these cows that we've described as desirable cows for grazing that have good capacity for forage intake, for lower quality roughages, etc. And we basically take those cattle and convert them to sort of gutted snowbirds as we feed them 10 pounds of a high energy dense diet. the supposition, or at least mine would be, that now we've got one with a much lower,
Are we going to wreck
gut
them when
mass.
we turn them back out, right?
yeah. So do you think that, again, it's just that environmental impact and the change of visceral mass of visceral organs that accounts for a large proportion of that change in, or decrease in, maintenance energy requirements?
Well, Mr. Trubenbach, who's here in the room, sitting right behind you, Dr. Horn, has great interest in actually trying to test that specific hypothesis. It's just really expensive to do, so I'm resistant right now. Hypothetically, though, we would say that a substantial portion of that reduction must come from reduction in visceral tissue. The other thing, though, that we may be overlooking is the heat increment effect, because as we switch from these high roughage, say a great predominantly forage-based diet to a predominantly energy-dense diet or concentrate diet, and simultaneously reduce total DMI, there's definitely a heat increment of intake reduction that occurs there. So, and it may be as much as half of that total reduction. We can't measure it that precisely, to be honest, but that's my supposition.
One of the things you do when you confine a cow on a higher energy diet, and by the way, if you confine a cow on a higher energy diet from a pasture program, a conventional one, you change their body shape. I mean, their gut, if you will, gets smaller, their barrel gets smaller. Mm-hmm. To the trained eye of the person that had them out on grass, he really doesn't like that very much. So we had one place, we took some cows for some people, and they said, do what you think works, because we don't have any feed when you do this. And anyway, they came to pick them up, and they said, I think you ruined my cows, because they look so different, Well, give them 30 days back on the grass, they look like they did before.
Right.
But what you're doing, and now this is a guy that's prone to give horseback opinions, but I think what you're doing by reducing that gut size so much, and you also do reduce the liver size, and these are the two most metabolically active organs, I think, in the body, or I think somebody here may know that for sure, but I believe they are. When you reduce gut size and liver size, you reduce metabolic requirements. I mean,
Sure.
You really drop maintenance requirements, because these are very actively metabolically active tissues that require a lot of energy to run.
And I think too, the follow-on, the concern perhaps is, are we causing a change that's irreversible? So again, the way we've envisioned this system, we expect those cows to go back outside. They're going to be outside more than they're inside. And so are we creating an irreversible condition in which those cows can no longer cope with that other environment? Well, currently I would say no. Part of why we have the Red, White, and Blue project is to be able to evaluate that over a longer period of time. The reason that we would say no is in part based on some of the work out of Clay Center, looking at realimentation and transitioning between high and low levels of consumption, and what they've observed with regard to heat expenditure, which would suggest that plasticity is bidirectional, right? That they'll recover that gut mass as needed in order to cope with that change in diet. That's also consistent with what we observe feeding packer cows. And so, this, and Spencer Swingle and others, many years ago, looking at realimentation of thin cows. The other thing that we found to be really interesting is that we expected the cows to look really hooked, right? To really look pinched and thin. They really haven't. Now they're definitely slat-sided, right? They're not full. like you would expect in a cow that is consuming dormant forage, but they don't look emaciated, and our cows have preserved condition throughout. In fact, our bigger challenge is probably the cows getting fat. And so right now I would say that, well, I mean, we have the concern, we don't anticipate it being a problem. We do have a couple of experiments, one that's actually already been conducted, but it got finished 2 weeks ago or 10 days ago, and so I didn't put data in about transition, because, you know, I'm actually more concerned right now, can we take a cow that's been just on forage, put her straight into the yard and just go to town with her, or do we have to adapt her? And we're doing it with no adaptation. So we have an experiment to evaluate the risk of that, and we look for sort of a continuing observation to see whether we're creating a longer term problem by what we're doing.